Hello, everyone. My name is Callen Votzke. I am a PhD student here at Oregon State University, and today I will be presenting our paper, Auger-Based 3D Printing of Stretchable Liquid Metal Paste Interconnects, a brief tutorial, here at IEEE FLEPS 2021. So your first question might be, okay, what's a stretchable interconnect, and why do we need a stretchable interconnect? So really what we're looking at here is making stretchable circuits. Your standard circuit board is made of fiberglass and copper, whereas our circuits are made out of silicone and liquid metal. The idea being that you can stretch, you can strain, you can deform these circuits in any way, shape, or form, and they will survive. But so why do we need to make circuits stretchable? And the idea is that if we want to make truly wearable devices or electronic skins or even soft robots, we're going to need to be able to make electronics that are free from the rigid little boxes that electronics love to live in and have them sort of distributed throughout the body and in such a way that they don't interfere at all with the actions and motions of the wearer. If we take a look here, for example, at the soft robotics side, the idea being that we have this quote unquote soft robot, but a lot of these pieces are very hard and they're just rigid valves, rigid compressor, and really only the actuators are soft. And our goal is to be able to make a soft robot that really is just as soft as can be. The sort of gold standard is from nature and is the octopus, because an octopus can fit through any orifice large enough to fit its beak, which is the only rigid part of the robot. And if you think about making a sort of large scale body network, most of the area will be in the interconnect itself and not sort of the circuit area, the active circuit area. So we need these stretchable interconnects. In order to make stretchable circuits, we need stretchable interconnects. One of the ways to do this is by using your standard solid metals and patterning these deformable geometries, such as the gold serpentine ribbon wire shown here, which essentially just stretch out as the circuit is strained. Another way of doing so is by using sort of silver nanoparticles or similarly conductive particles in conductive inks. Those inks are then cured and usually sintered together, and you get a percolation network rather than sort of direct conduction, but that provides a stretchable interconnect nonetheless. Our work focuses on gallium as a liquid metal for stretchable interconnects. It is liquid at room temperature, has good conductivity, about 1/10 that of copper. The only downside being that as a fluid, it's rather hard to pattern. What we do is instead modify the material properties of the gallium to make it into more of a paste-like consistency. When you add in nickel particles, you can essentially create something that's more like toothpaste and is actually able to be dispensed from a syringe. While the liquid metal paste is able to be dispensed through a syringe, it turns out that using the normal directly pneumatically operated syringes causes a number of problems for fabrication. One of these is that when you're trying to make short circuit traces or long circuit traces, you really only have on and off control of the syringe. The air pressure can either be on or it can be off. There's no real middle ground. The air pressure has to be a certain level in order to effectively shear the material and push it out the nozzle tip. Any lower and you will not be able to generate the shear forces required. And if you dial it too high, then you will essentially empty your entire syringe in a single shot. The problem is that once that air pressure is dialed in, it is only dialed in for that particular fullness of syringe and for that particular batch of liquid metal paste. Ideally, you'd be able to vary the syringe pressure throughout the entire process, but it's nearly impossible to know exactly the syringe pressure you'll need a priori. Thus, it's kind of difficult to use. Also, when you are making a lot of short circuit traces, The pulsing the air pressure on and off quickly actually causes the nickel particles to separate out of the liquid metal, leading to nozzle jams, which just completely end your printing for that moment. By comparison, what we're using now is an auger screw. So this is essentially your classic Archimedes screw in that you're now moving to sort of a volumetric dispensing. When you turn the screw, it moves a certain amount of volume of the liquid metal paste. Thus, if you turn the screw slower, the paste is extruded slower. If you turn the screw faster, the paste is extruded faster. This is much more useful than a on and off control like the pneumatic syringe. In that, especially say, once you're rounding a corner, you don't want to have a constant output rate because the printer will actually slow down ever so slightly while going around the corner. If you kept up at a constant output rate, you ended up with a giant bubble of material right at that corner. By comparison, if you can slow down the material ever so slightly when going around the bend, you can create much thinner, higher resolution lines. In order to print the material, we have attached an auger screw onto a custom-made head for a Lulzbot TAZ 6 3D printer. While this printer was originally made to extrude molten plastic, we have repurposed the stepper motor from that head that allows us to turn the auger screw. The auger screw, as you can see here, is made up of a couple of parts. You have the screw itself, the very tight-fitting auger body that is fed in by a pneumatically operated syringe, but the pressure is constant through the entire print, so it avoids a lot of the on-off problems that we saw earlier with just the syringe itself. And the stub nose nozzle tip. By using the very short nozzle tip, we're able to reduce the amount of back pressure in the system and generate a much nicer flow of material through the nozzle tip. But by using this original stepper motor to turn the auger screw, we can take advantage of all the advancements in process optimization and print planning for molten plastic. All you have to do is just set a extruder multiplier of 10 in your slicing software, and it takes it from there. Additionally, in order to counteract any waviness or just non-level in the base silicone sheet that we have to print on top of, because your standard liquid metal circuit essentially is a sheet of silicone, your liquid metal traces, and then another sheet of silicone that is poured on top and allowed to solidify. That generates a fully encapsulated circuit and essentially microfluidic channels that the liquid metal lives inside. The bed leveling sensor allows us to sample the bed at 16 points and gives us the ability to compensate for any unlevelness or waviness in the bed. So here's a video of the extruder in action. You can see it turning. This is actually a slightly earlier version before we had the bed leveling attached. And as you can see popping up in the background here, there is a print that failed due to the bed not being level. So there's a number of errors you'll see when you're printing. This is certainly not a perfectly refined process. You have the most common sort of staccato error, where you get what should be a continuous line printing intermittently. Usually that's just because your nozzle is too high. A bulge failure, which as you see here, or in the various bits here, essentially the paste has gotten to be a little bit too thin for printing and too much material is dispensed. This can sometimes lead to lines being bridged. You have the wavy failure where straight lines print with sort of a sine wave instead, the leveling issues, or when the paste completely fails to extrude. And these are discussed in more detail along with suggestions for how to solve them in the paper. As an example, here is a printed 2.4 gigahertz Bluetooth antenna, as well as a self-reading strain sensor. So this is sort of an example of our process, how the liquid metal is printed onto the silicone rubber. The active and passive components are placed, and then the entire circuit is encapsulated in a layer of silicone. And here we can see the circuit stretching and able to detect its own deformation. So in conclusion, we have converted an off-the-shelf 3D printer into a auger extruder for our liquid metal paste, but also potentially being able to use for any material with high or especially inconsistent viscosities, as the auger is rather immune to any changes in viscosity because a turn of the screw results in the exact same volume being dispensed as every other turn of the screw. We have also discussed common failure modes and likely troubleshooting steps. The authors would like to thank the Semiconductor Research Corporation for their support, without which we could not have done this work. Thank you very much.